In this video, we will cover an example of exact equations. We have tangent x minus sine x times sine y dx plus cosine x times cosine y dy equal to 0. Now, step 1, we have to ask, could it be exact? Well, first, is it of the following form? M dx plus n dy equals 0. Indeed, it is, because we recognize our m and we recognize our n. Now, if it is of this form, the next question is this a differential of a function f of x and y equal to a constant c? Well, if so, then it is exact, but we have to prove that. So step 2 is it exact? Well, in order for that to be true, then the m will have to be the partial of f with respect to x, and then n would have to be the partial of f with respect to y. And of course, both partials have to be continuous on some region in the xy plane. And the way we prove this is we go ahead and solve for this equality, where the partial of m with respect to y has to equal the partial of n with respect to x. So we go ahead and plug in our m and n. We get the following. Now, the left side, you're taking the derivative with respect to y. So essentially this goes to 0 because it's treated like a constant, assigned in terms of y. And on this side, you can think of the sine x as a constant next to this function. So essentially we're just taking the derivative of sine y. So we get the following. Now on the right side, we're taking the derivative with respect to x. So now the cosine y gets treated like a constant, and essentially we're just taking the derivative of cosine x. So it becomes negative sine x cosine y. We see that both sides are equal, so this equality holds, and indeed this equation is exact. Now for the next steps, there's two ways we can go about this, so let's do a quick recap on what we mean by that. So right now, we just finished this step. We just proved that it is exact. Now, there's two ways we can go about this moving forward. We can go through steps 3 to 6, and if that doesn't work out, we can try 7, or we can jump straight to 8. The idea is this. Steps 3 to 6, you're essentially just picking one partial, and you're solving for it. But the process of solving it is a lot longer than doing both partials in step 8. So basically, the idea is that if you have a partial that is a lot simpler than the other, then you go through these steps. But if both partials are rather simple, then you can just integrate both partials, and the solution will be the overlap. Now, in our case, we can see that one partial, n, looks sort of simpler than m. So what we're going to do is do steps 3 to 6, where we pick the partial of n and solve for that. So proceeding with this, we pick simpler partial. Of course, it was n. And then we go ahead and integrate that with respect to y. So we get the solution f of x of y. We get the constant of integration h of x on the outside. This is in terms of x because the constant is always in terms of the other variable that we integrated. We integrated with respect to y, so the constant of integration is with the other with respect to x. We plug in for n. We solve for n. We get this. Now the next step is we want to differentiate the other to get the other partial. What we precisely mean is we want to differentiate with respect to the other variable. So in this case, we differentiate with respect to x. And in doing so, we should get m, because df dx equals m. Now, we just solved for this integral right here, and it came out to be cosine x sine y. So then this shall become negative sine x sine y. And then this shall become h prime of x in short. Next step is step 5, is we go ahead and isolate the integration constant, and we integrate that. If we rewrite this previous equation, but isolate for h prime in short form, it shall look like this. M minus the derivative with respect to x of integral of n dx. Rewriting that, but with all our terms plugged in, we get the following. The sine x sine y cancel, and then we have h of x equal natural log of secant x after doing the integral, because the integral of tangent is natural log of secant. Step 6 is we can substitute the integration constant and we can simplify. So in doing that, we substitute this back into here. We get the following. Now, this is pretty much of our solution, but we have to write it in terms of set to a constant c, and now we have our solution. One way we can verify that this indeed is our solution is going from this and deriving m and n. So remember, df dx equals m. Plugging in for f, we have this, and then solving this, we get this. And this indeed does equal m, so we have verified for our m. And then we try to verify for our n. Plugging in for f, we get this, and solving, we get this. And this indeed is our n, so we have verified both, and this completes our problem.